So yeah, hi. I haven't given a talk in person since 2018. So this is, well, I defended my thesis, but it was different. It was in Spanish, so it was easier. So yeah, so I'm Anna. I started here a couple of weeks ago, and like Mike said, I'm a new postdoc at WCA and FPI. I come from Argentina. I did my everything, my PhD, and we have a licenciatura, which is like a master's at Universidad Nacional de La Plata, and I also spent a year at ISO as a student. So I'm going to tell you a bit about what I did during my thesis. This is one of the many titles that my thesis had at some point. This is not the title it ended up having, but this is the most comprehensive one. So I'm going to tell you about how I've used discrete tracers, what I've done with them to try and understand a little bit more about the evolution of early type galaxies. So I'm going to do a super brief introduction because I think everyone here is pretty acquainted with galaxies. And then I'm going to tell you about the two main types of tracers that I used and they're mostly used, which are globular clusters and planetary nebulae. And specifically in globular clusters, I'm going to tell you a little bit about the two different approaches that we've used. So yeah, so early type galaxies, as you probably know, are galaxies which are very old and have their star formation has been quenched for quite some time. And morphologically, they are mainly ellipticals and lenticulars. They are commonly called red undead, which is kind of a horrible nickname because it makes them sound very boring, and they are not boring at all. So I hope I can convince you. And what people agree on at the time is that their formation happens in two big phases. We have a first phase, which there's a gas infall and the galaxy accretes that, and then it forms a bunch of stars. And then at some point it stops forming new stars, but its mass continues to grow through the accretion of satellites. So we have mainly dry mergers in this second phase. There's not a lot of new stars forming, but the galaxies can grow up to many times their mass just by accreting, eating every other galaxy that they find. So we're going to focus on the second phase of the accretion because this is the one that is usually traced by looking at the stellar populations of these types of galaxies. Stellar populations are really cool because they are basically fossil records of everything that the galaxy has been through. We can look at them now and try to see what they can tell us about the story of the galaxy. But the problem with stellar populations, which is not really a problem, but the thing is that we can only see them under certain circumstances. If the galaxies are too far away, it's really hard to resolve stellar populations. We cannot see like star by star, we can just see integrated light. And then even in galaxies that are not that far away, if we want to look at the extended halo of the galaxy, so like just move from the center region, we find the surface brightness becomes very low very quickly, and we cannot really see a lot of the stellar population, even though we know that it is there. In this case, we need the help of my beloved discrete tracers, which are basically any object that they have to be related to stellar populations in some way. They have to be very, very bright so that we can see them where we cannot see the stellar populations. And they have preferably to be compact enough so that we can resolve them at large distances. This is just an example. Work I had nothing to do with, but I really like the plot because it shows the work by Napolitano collaborators from this year. And what they do is they look at the Fornax cluster, where we know that there's a lot of galaxies and they are probably interacting in a number of ways. And usually when you want to see if a galaxy is interacting, you can see structures in their low surface brightness profile. Sometimes you cannot see them, but it doesn't mean that they're not there. It just means that they are very low. So what they do is look for all types of discrete tracers. Here, all of the green dots are planetary nebulae and globular clusters. They just bundle them all together. And the idea is to see by looking at their overdensities, they can find streams that show us some interactions between galaxies. So for example, this is one of many plots like this that they have. This is the region of the Fornax cluster. We have a slightly massive galaxy there. And then we have all of these green dots here that are signaling the presence probably of a stream, just to make me nervous. Okay, so it's pointing to there's probably a stream here that is connected to these blue squares and circles, which are dwarf galaxies. So the idea is that with this, they are showing that there might be some chance these dwarf galaxies have interacted with one of these more massive galaxies. They are losing stars, including globular clusters and planetary nebulae, as they move through the cluster. So this is just to show you that discrete tracers are useful.
Sorry, what are they doing? Circles?
It's just globular clusters and planetary nebulae, anything that they count as discrete tracers. So the main type of discrete tracers that I worked with are globular clusters, which are the coolest objects in the universe. It's just facts. Globular clusters mainly look like this image we see here in the bottom, if we could see them very up close. Usually when we look at Milky Way clusters, we see them like the upper image. The way I see globular clusters, which is at extragalactic distances, is kind of like this. This is the Gemini image of a galaxy that I studied. And globular clusters are just these little dots to me. So they are basically like a star in my perspective. They are just little balls of stars. They can contain up to hundreds of thousands of stars. They are very, very massive stellar systems. They are very, very compact, and this makes them very, very bright, which is what we want in a discrete tracer. And the main way in which they help us figure out stuff about the galaxy evolution is based on the fact that they are very old. Most globular clusters have ages that are pretty similar to the age of the galaxy that they are hosted by. So they both got a chemical record of properties of the galaxy at the time that it formed, because they formed at the same time. And they also have, we can find in the properties of a globular cluster system of the galaxy some information about the processes that the galaxy went through, because the globular clusters have survived it all. If you can see them today, it means that they managed to survive whatever mergers and interactions the galaxy went through, but they've probably been affected by it. One of the main properties that we study in globular cluster systems is the color distribution. I'm just going to mention this one property very briefly because it is very debated. The idea is that if you look at basically the combination of two filters, you can see what colors the clusters have, and you can see how many clusters you have per color interval. In general, globular cluster systems tend to present a bimodal distribution. This means that they have blue globular clusters, which are considered to be slightly poorer in metals, even though all globular clusters are very poor in metals. And they have a red subpopulation, which is considered to be rich metal. This is very debated because the color and metallicity relation is not beautifully linear. It has a lot of degeneracy with age. It has a lot of degeneracies with many things, but for globular cluster systems, usually we can at least say that if we find two different subpopulations in the color distribution, we can usually find that these subpopulations will also have different properties of other types. For example, red globular clusters tend to be very concentrated towards the center of the galaxy, while blue globular clusters have more extended spatial distributions. If you have spectroscopy, you can look at their kinematics, and they also tend to be different. So even though color is not an exact measurement, metallicity usually, we still try to see if we can find subpopulations because we've seen from their behavior that they exist. In some cases, you can even find, like in this work, it was done by my group, but I was barely even born. But we can see that they find an intermediate subpopulation over here, which they see has very specific properties. It is contained in a very specific interval of magnitude, and it is located in a very specific region of the galaxy, which indicates that it is probably, in fact, a third subpopulation that it might be a younger subpopulation. So this is usually how we find traces of recent mergers looking at globular cluster systems. So far.
So if you were gonna aid on these three populations, what would you say this one is how old?
The age difference is usually very small. Like most globular clusters are around, I don't know, I want to say older than maybe 10 giga years.
So these three, you think they're all older than 10 giga?
They probably have. I mean, I cannot tell you right now what age is estimated for the intermediate population, but they're not usually have to be much younger, because otherwise they would not have formed as globular clusters. It takes a very long time for them to reach that form. And it's very hard. I mean, this is a work that was only done with photometry. And if you only have photometry, it's very hard to get real estimations of this. So most of my work in my thesis was done looking at individual galaxies. The idea is that, yes, large surveys of galaxies are amazing and they are very useful, but studying at individual galaxies has a lot of perks because, firstly, if we want to build statistically significant sample of galaxies that have different properties, it's good to look at them one by one. And also, when we look at a galaxy in depth, we can find certain peculiarities that we might have missed if we were just looking at it among a larger sample. And these can pose new questions and provide us new constraints for everything that we know about just large-scale galaxy evolution. So, for example, one of the work that I did in my thesis was looking at this galaxy, which is called WCA 1172. It's a lenticular galaxy. It's an intermediate mass one, and it is located in the field, the lowest density environment. And the motivation behind studying this galaxy was that there's a previous work by Cho and collaborators from 2012, where they look at a sample of galaxies. They're basically looking at isolated early type galaxies, and they are characterizing their globular cluster systems. And among them, they look at this one and they say that this galaxy seems to have two peculiarities in its globular cluster system. One of them is that the color distribution seems to be narrower than most globular cluster systems color distributions. And also that the specific frequency for this galaxy, which is a parameter of globular cluster systems that we'll look into in 2 slides, it is very, very high for a galaxy of this mass, specifically considering that it is located in such a low density environment. The issue is that this work uses ACS data, which is great quality, but also it has a very small field of view. So when you want to quantify globular clusters, you have a very small field of view, you're going to have to extrapolate quite a bit. So our idea was to go look at this galaxy again, but using larger fields of view, basically. So we had data from GMOS at Gemini, which has larger field of view than ACS, and we also got to have 3 fields, so we covered quite a big region of the sky. We used 4 filters, also so we would have a better look at the color distribution. And then we used near-infrared data from Forstar, which has a huge field of view. So what we find when we look at all of this, first we look at the color distribution. We can see that we can basically build color distributions for any color that we want to try. And the idea would be that if we find bimodality in one, we should find it in all of the colors. This doesn't usually happen because the relation between color and metallicity is very complicated. What we find in this galaxy is pretty rare, because usually what happens is that when you look at colors that are built from filters that are closer together, usually that diffuses the bimodality. So when you go to filters that are further apart, you should find a clearer bimodality. Here we find the exact opposite, because G minus Y are much closer together than G and C set. And we see that G minus Y gives us a very nice bimodal distribution. This is statistically significant. We run our tests. That's very nice and pretty when we go to look at G minus Z. The distribution is very weird. It's not really unimodal, like statistically, but it's also clearly it's not bimodal. So that's one strange thing about it. And we also find that the result by the previous work is confirmed. Usually the ranges in G minus 5 for globular cluster systems go between 0.5 to 1.5. This one goes between 0.7 and 1.2, which is quite narrow for this for a galaxy. But one thing that we find is that when we look at the literature, we build this graphic here on the top right, where we have the difference between the 2 peaks in galaxies that were found to be bimodal versus the absolute magnitude. These are basically all the early type galaxies for which we found this information in the literature. The green triangles are also galaxies in the field. And this black triangle down here is our galaxy. So what we find is that, yes, it does seem to be narrower than the others, but also there's not a lot of intermediate mass galaxies that have this information available in the literature. And there could be a trend where this is a work in progress because it's hard to get a trend because all of the data comes from different sources. So it's hard to get the errors that match. You'll hear from us. Okay, and so because we have this issue where we don't really know what's going on with the color distribution, and we cannot really do a lot more with this because we only have photometry, we looked at this from two different approaches. On the one hand, we have now acquired spectroscopic data, which we will use to actually have a better look into what the metallicity is for the clusters in this galaxy. That is very much in progress. I only downloaded the data. It's a very long time. It's very hard to get spectroscopic data for clusters at distances of something like 19 megaparsecs. But what we also did was, since we had all of these filters, we could build a lot of colors. We can combine them all as we wanted. And there's a lot of, well, there's quite a few globular cluster systems for which we have actual metallicities obtained from spectroscopy. So we used all of this to try our hand at Bayesian analysis, and we managed to calculate photometric metallicities. The idea is that once we have the spectroscopy and we can see what the spectroscopic metallicities are, we can go back to this and see this approach, which has not been very much used in the literature, is actually giving us good enough results. So the other thing that we look at in 1172, like I said, is a specific frequency. The specific frequency is a parameter that can be quantified in relation to the mass, the stellar mass of the galaxy, or to the luminosity of the galaxy. It should give us a similar idea, basically, of how efficient the galaxy has been at forming globular clusters in relation to how efficient it's been at forming stars. Kind of the main idea of specific frequency. The distribution of specific frequency, whether in whichever format you want to look at it, when you compare it to their stellar map or magnitude, tends to be U-shaped. These are all early type galaxies from a catalog by Harris and collaborators. It tends to be very U-shaped, and it has a very, very universally agreed on minimum for the specific frequency at a mass that corresponds to the mass of this galaxy. This galaxy, instead of being at that minimum, is pretty high above these axes are, that axis is logarithmic. So it's kind of deceiving, but it gives us very, very high values for one for a galaxy of this mass, because intermediate mass galaxies tend to have pretty low values of specific frequency. And for a galaxy in the field, it is pretty weird that it has formed such a high number of globular clusters in relation to its field stars, because it doesn't seem to have been affected by any mergers or big interactions. It's a pretty normally behaved galaxy. So this is the work that we did just to match those results, and we're going to look at the spectroscopy later on and see if we can find out why this is all happening. So far, all I know is that it is happening, I think. So another galaxy that we looked at. Yeah.
Was there a reason you picked this galaxy to look at?
Yes, because we looked at this work by Cho and collaborators and found this very, very high specific frequency. But the specific frequency that they had, I mean, the value, say it was something like 9, but the error was like 5. So it was either a very peculiar galaxy or it was just a large error. So here we reduced the error to something like 0.5, and we confirmed that this value is real and that it's worth looking into.
What about these other points? What are the errors on those? Are there?
Yeah, I mean, these plots are kind of hard to see maybe in this format. There isn't a lot of error when you go to the intermediate mass. Like this is really, really high, even if you consider error bars for the values of this galaxy.
Curiosity, if you convert this stellar mass into the halo mass, did you then find that this U-shape goes away?
I don't know the answer to that. It's a good question. I don't think I've ever seen it because since it comes calculated on the basis of the stellar mass. I don't think I've ever seen it in relation to halo mass, but that's interesting.
Seminal paper by Harris, and Hudson, isn't that?
I was going to say.
Sorry.
I think at least one of the edges, or maybe two of them or three of them are on the Zoom call. I don't know how many of them. I saw Bill still there.
It's totally flat. It's a universal constant.
Okay, good.
Okay, so I'm gonna move on to our next galaxy. So this is NGC 3640. It's a very nice galaxy, which has a lot of weird stuff going on. It's a work it's been in progress for longer than I thought because I had to write a thesis in the middle. But we looked at this galaxy because there's a work by Brunel and collaborators from the 80s where they just look at this galaxy for some reason using a 2-meter telescope, big humidity, and they find, if you see that first image over there, that's the image of the galaxy, but the surface brightness profile has been subtracted. So what they find once they take out the surface brightness profile is that they find a bunch of structures, we call them patchy shell-like features, and they associate all of the structures in the low surface brightness with a merger that could be in progress. After this was published, this galaxy started to be included in a bunch of samples of people that were looking at galaxies with weird stuff going on. And the work that was done after that usually estimated an age for a merger between 5 to 7 gigayears ago, so not that recent. But the thing about this galaxy is that you can see here, this is all from Brunel, and they identify all of these structures. They say it might be a major merger because the idea is that usually shell-like features are associated with major mergers. But all of the works that were done on this galaxy focus very much on NGC 3640 and the potential major merger like it had, and they always at the end mentioned that NGC 3640 has a compact elliptical companion, and they could be interacting or they could have interacted, but no one really moved their field of view a little bit in the direction of the companion to see if there was any connection between the two of them, which is not unlikely because NGC 3641 is a compact elliptical, and from my very brief understanding of compact ellipticals is that they usually have been interacting with a larger galaxy. So what we did was got 2 Gemini fields for on this picture so that we could look at both galaxies, look at their globular cluster systems, and see what we could learn about what's going on with them. They have, I mean, redshifts, it's all very, very low redshift, but if you look at their systemic velocities, the errors in the calculations are very large. So it really depends on what paper you look at, which is also, I think, why all of the previous works have either said, like there's works that say these galaxies are very, very close together, and these features are because they are interacting, and then the next work will say, no, that's impossible because these galaxies are very far from each other. We don't just have photometry, so we cannot really add too much to that. So the first thing that we did was also remove our the galaxy from our image, and we found the same structures. These images are not in the same orientation, but if I turn them, they look super weird. So let's still show them normally first. We find basically the same shells that they find. It's not very surprising. And then we go look at the clusters. We cannot really separate the clusters from that one galaxy from the other because we don't have velocities. So the best we can do is do a preliminary separation just spatially and see what happens if we find anything. So we got all of the clusters that were very close to the more compact galaxy, and we consider them as her clusters. And then we got all of the others in the field and said, okay, let's assume that they are NGC 3640 clusters and see what happens to the color distributions. What happens is mainly that when we look at the entire color distribution for the clusters that we consider to be related to 3640. It's statistically bimodal. There's stats are very good. They're very nice. The weird part is that even though I said red clusters are usually more concentrated towards the center and blue clusters are usually more extended, here what we find is that if we only look at the central region of 3640, we'll find only red globular clusters. And if we look at the outer region, we just basically find blue globular clusters. So what's weird about this is that there's basically no blue globular clusters in the central region, which is not really common. NGC 3640, or at least the globular clusters that has very close to it, are mainly just red, which is not very surprising because if it has interacted, usually galaxies tend to lose their blue globular clusters first. When they interact, when a smaller galaxy interacts with a more massive galaxy, it wouldn't be weird if someone had stolen their blue globular clusters. It is kind of weird that we don't find basically any blue globular clusters here either. I did this photometry like 3 times because this is our kind of weird results for the color. And then we go look at what's happening with the spatial distribution, because clearly there is something going on, or we wouldn't be finding this difference in the regions. No, that was really fast. So what we did was just look at the spatial distribution for all blue globular clusters found in the field. We're no longer separating between what we attribute to each galaxy. And we plot here over the residual image, we plot these contours, which are isodensities, basically. So the darker the contour gets, the higher the density of clusters is. When we look at these contours, what we see is that the blue globular clusters seem to follow the larger features in the low surface brightness distribution of the galaxy, which might be telling us that whatever event caused these shells might have affected the spatial distribution of the blue globular clusters. And this might be part of the reason why we don't have a lot of them in the central region. It is a very strange result in a way, but also it's very encouraging because it's nice to find a connection, a direct connection between vital features and blue globular clusters. The red globular clusters are more evenly distributed, but we do find that they are, if we consider all the red globular clusters in the field, including the ones that we attributed to the other galaxy, we find that they are mainly located in the region between both galaxies. So there could be some interaction going on there. Again, everything here needs further work because photometry can only take us so far, but this is very nice and interesting. And hopefully I'll have further analysis once I sit down and write this paper, but it's still a nice result. Yeah, so another way in which you look at, yeah.
It's hard to break it. Have any way to test that those clusters maybe formed earlier at the same time as the shell? Or, I mean, not earlier, formed later.
It would be weird for blue globular clusters to form later because they are very poor in metals. So usually you would expect them to be older. No, that's, I mean, they're globular clusters, so they're never going to be, when I say blue and red, for people who are not in globular clusters, this is also just very blue. The red clusters are quite blue because they're all old stellar populations. It would be hard for them to be detected as globulars if they were that much younger. Usually when you do find young globular clusters that were formed in mergers, those are apart from the bimodal distribution that you usually find. But it is very hard to get that much detail from photometry. But if you want to do spectroscopy, you have to convince someone to give you that much time. So this is good for that. Yeah, and then another way in which we use globular cluster systems was rather than, yep.
Can I just ask one thing?
Yes.
Yeah.
Yeah, just if you go back one slide. So those don't look like shells to me. Those look like tidal features, right?
Yeah,
And the globulars, the blue globulars, at least some of them look like they sit right on top of the tidal features. So, I mean, is an explanation of this not just that this is a disrupting lower metallicity smaller galaxy, and that a lot of the blue clusters are just its clusters?
yeah. I mean, firstly, I'm stuck kind of using shells because that comes from that paper from the 80s, and I've just adopted the word, but they are indeed tidal features.
I mean, you
That
can
is-
see there's a wrap towards the lower center of the left-hand image. You can sort of see there's a caustic where something's turning around, right? And it's not round, it's angled, which is, you're seeing you know, basically a tidal feature projected at some angle. So yeah, to me, the fact there are sharp angles in there, that looks a lot like you know, tidal debris from a specific single galaxy getting disrupted.
Yeah, I think that's the likeliest explanation. It is kind of strange that we don't really find a lot of other blue globular clusters other than the ones that are associated to this tidal feature. So that's
Right.
causing some debate.
I guess also it's odd. I don't understand what all the red ones are doing at the top of the right-hand image.
I mean, we also have the companion galaxy up there. So a lot of
Okay,
those
so
clusters
I
are from
see.
that galaxy.
Sorry, so it's been subtracted as well.
Yeah, yes, they're
Oh,
both
I
subtracted.
see. Okay. No, that makes sense. So you've got 3 galaxies in the picture basically, and one of them is being disrupted and is producing all the blue stuff. Yeah. Okay.
Yeah,
Or a lot of it. Okay, thanks.
no problem. Okay, so globular cluster systems, part 2. We also looked at, rather than individual galaxies, we looked at the globular cluster systems of larger samples of galaxies and tried to look at how the properties of the cluster systems are related to the properties of the galaxies. We expect to find a relation because the way that globular cluster systems are formed is usually very closely linked to the emerging history of the galaxy that hosts them. And one of the main things that we look into when we look at scaling relations is the size of a globular cluster system. To get the size, what we do is get a radial distribution. We see how many clusters we have per radial bin, and we extrapolate it, and that gives us the total extension of the system. We are, within my group in Argentina, we've been doing some work. We've published 2 papers already, and we are working on the next one. And within this large project, we've done slightly over 100 galaxies so far that cover a wide range of masses and environments. And we've seen a few things. I'm just going to show you very few results. I want to talk about all of my discrete tracers. But these are from our paper from 2021. On the, over there, I don't know if to say right or left. There, on the first part of the slide, we see we have TN, which is the specific frequency in relation to mass that we mentioned earlier, which basically talks about the richness of the globular cluster system and the efficiency of formation. And we see, compared to scalar mass, like we saw before, here the colors and symbols. I think this is kind of a confusing way of signaling it, but I didn't do this plot, and I don't want to. I hope no one's hearing it, but what's involved. The idea is that the gradient in color goes from less dense of an environment around the galaxy to more dense, so from yellow to blue. The idea was to also add the symbols because otherwise it was kind of confusing. I think maybe, but yeah. So yellow are galaxies that are in lower dense environments, and blue are in higher density environments. The little stars are very low mass galaxies, and some galaxies, I don't know if you can really see it, but some galaxies are highlighted, so the lines of the symbol are thicker, and those are central galaxies, while the other ones are satellite galaxies. There's a lot going on in this plot. So the main thing that I'll show you, there's what we see is that if you look at the one below, you can see The first one is for satellite galaxies, and this one is for central galaxies. The central galaxies have, for higher density environments, have higher values of specific frequency, and then there's a trend that goes downward. So as you go to lower density environments, the specific frequency goes down. For satellite galaxies, the trend seems to be the other way around. So galaxies in higher density environments have less populated globular cluster systems than satellite galaxies that are in lower density environments. That's kind of confusing, maybe, the way I said it, but the idea is that satellite galaxies, when they are in higher density environments, are more likely to lose their clusters. So they're going to have less, basically. And if you have central galaxies in higher density environments, they're creating a bunch of globular clusters. So this result makes sense. These are relations that had been studied, but we extended the sample towards lower masses and higher masses, and we added a lot of points to the relation. The second one is the extension of the globular cluster system. So how far from the center of the galaxy we still find globular clusters in relation to the stellar mass. We find the bilinear relation. There's many different fits for this relation throughout the literature. With all of the galaxies we have, we find the bilinear relation is reasonable errors. And again, what we find, if we look at the plots below, like better, is that if you look at the satellite galaxies over there, you can see that galaxies that are in denser environments have smaller globular cluster systems, which is a result that is consistent with the previous one. And then the work we're working on, the analysis that we're performing now, we're looking at a different property of the radial distribution of the globular cluster system, which is the core of the globular cluster system. The idea is that we have this parameter, R0, which gives us an idea of how many globular cluster systems we have in the central region of the galaxy. So for the first plot, what we have on the y-axis is the field radius of the core of the GCS. So how large how many clusters we have in the central region, in very simple words, in proportion to the radius of the galaxy. And we have that against the stellar mass. What we find is that there is a spread, but most of the galaxies seem to be concentrated towards one, which implies that there is a proportionality between these two quantities, which makes sense if we consider that galaxies and globular clusters have a coeval evolution. A more interesting result that we are still working on, because I am reducing all of these galaxies and it's taking some time, but I put all of the ones that I have on red and in these red dots, and all of the blue ones are the ones that we had from previous work. And we find that if we look at the scale radius of the core against the central velocity dispersion, at lower values of central velocity dispersion, there doesn't seem to be much of a trend, but it does seem to go higher as we go to higher values of central velocity. So the idea here is that if we have higher values of this parameter R0, that means that there are less globular clusters in the central region of the galaxy. So if we have higher velocity dispersion in the center, we have less globular clusters. This is interesting also because this parameter of the central velocity dispersion seems to be independent of the environment. So this would indicate that this parameter of the core would also vary in a way that is independent of the environment and would just be dependent on the merging history of the galaxy, which is what affects the velocity dispersion the most. There are not enough dots, I think, in this to get a proper trend, but the ideas does seem to be there, and this is something that we are working on.
How did you find the scalar radius?
When you fit the radial distribution, we fit Cerseic profiles to this radial distribution, and we fit two parameters, which are basically the scale radius and another one, which I cannot remember right now.
Cerseic was the one with, remind me which one was Cerseic. Basic profile. What is it?
It's a profile we use. I don't know. I don't know what answer
It's
to.
like exponential and like R to some power and.
Okay, exponential of R to the
Yeah.
one part. Okay.
The one has the M.
I got it. Right. Right. Okay, thanks.
The R0 has to do with how low this profile goes in, how it flattens towards the center.
Is completeness a concern? I mean, the central.
Completeness is always a concern when you're looking at this type of thing. We did a very, very high number of tests for completeness. I think that's going to take its own paper because getting the completeness for this and making sure that it really does reduce the errors was very hard. It shouldn't be a concern because we did a lot of tests. The motivation behind this work is basically that in our group, we have looked at the radial distributions of many globular cluster systems, and they always seem to flatten towards the center. And there is always a discussion whether it's an effect of tidal erosion or if you just did your completeness wrong.
So if you inject fake clusters, you recover the clusters.
Yeah, we'd basically do that a million times, trying to follow the expected radial distribution for the clusters with our fake stars, getting the PSF to do a completeness test when you're using HST images. It's also hard, so we get that from other images. But the idea is that because it's HST images, completeness should be less of a concern than it is when we look at central regions in Gemini images. That makes sense. Okay, so I think that's all my clusters. Okay, so I'm going to quickly move on to the other side of my work, which is doing discrete tracers, but instead of clusters using planetary nebulae. This is the work that I started doing last year at ISO. And for planetary nebulae, what we call the phase that some intermediate and low mass stars go through during the last stages of their lives. And the thing that interests us at an extragalactic distance of planetary nebulae is that they are fairly easy to find. I don't want to say too easy and then jinx myself, but they're fairly easy to at least to identify because they have very peculiar spectra. We can see, for example, in this one that it's very much used. If you ever see another planetary nebulae talk, they usually put this spectra up. It has an almost null continuum and it has very intense emission lines. So what this means for us is that if we can just look at a galaxy using an O3 filter, and then we can look at that galaxy using a broader band continuum filter, usually what's going to happen is the planetary nebulae, as you can see over there, they're going to show up in the O3 filter, and they're not going to show up at all when we look at the continuum. So that's the reason they've been used as discrete tracers in terms of their detectability throughout the ages. These are the classical methods, and they have some issues, which is what I'm going to focus on. But then there's why would you use planetary nebulae in terms of their connection to the stellar populations. So the first and usually the most popular thing about planetary nebulae as tracers is that if we look at their luminosity function, number of planetary nebulae, and then versus the magnitude, if you look at this in absolute magnitudes, all the luminosity functions, most of the luminosity functions for planetary nebulae in other galaxies have a cutoff in the brightness that seems to be universal. So what this means is that we can use them to estimate distances. This is empirically, it's been seen across a very large number of galaxies. It is very much debated why this happens, because something we can see in this plot is that this seems to be a constant thing that happens across all Hubble types. So why this happens has given a lot of people who do stellar population, stellar evolution models a lot of work. And yeah, it's kind of a big question, but it does seem to be something that people use. Not the best standard candle we have, but it certainly works. Other than that, they're also used as kinematic tracers. As I said in the beginning, if we want to, when we look at galaxies, if we want to look at their extended halo, it's kind of hard to get spectroscopy and measure the kinematics of what's happening at larger distances from the center. So, for example, in this work by Crocato in 2009, you can see they have for this galaxy, we have just two different angles to combine them. But the idea is that we have all of these dots in the center, which are the measurements that they get from the stellar population. And then all of these ones are the ones that they get from planetary nativity. So we can see that planetary nativity allow us to extend our kinematic tracing up to very large distances. And this is very important because we want to try to trace the rotation curves of galaxies. We need to go as far as we can. Yeah, there are many more uses to this. But the last thing that I am focusing on is that there seems to be a relation between the properties of the stellar population underlying and the properties of planetary nativity, and they seem to be connected through a quantity that we call alpha. It doesn't have any fancier name than that. Alpha is a parameter that is connected to the number of planetary nativity that we see in a galaxy, the volumetric luminosity of the galaxy, but also to the evolutionary flux, which is a way in which we can quantify the age of the stellar population overall, and the visibility time of planetary nativity in that galaxy at that time. There's a lot of parameters, but the main idea is that if we look at the surface brightness profile, I forgot again. This x-axis is just radius. If we look at the surface brightness profile of the galaxy, that we can see here in this gray dashed dotted line, and we plot the number density of planetary nativity on top. They're usually much like this. There's an offset between them. Usually planetary nativity are going to be higher up, but if you correct by the offset, you both find that the profiles are very close together, and also that this offset is connected to this alpha parameter. So these are proportional, and you can get this parameter from matching this profile. Throughout the yeah, right. Oh, okay. Throughout the literature, what has been seen is that if you look at the alpha parameter of galaxies versus their metallicity, you just look at the line dark blue dots here. The square ones are the spiral galaxies, the round ones are ellipticals, and the fine ones are the irregular ones. There seems to be a relation between the alpha parameter and metallicity throughout all Hubble types. This is something that has been studied a number of times. But what has been done more recently is looking at galaxies that we can see maybe in greater detail. And if we find galaxies that have different behaviors in the central and outer regions, usually you can calculate an alpha value for the outer region and the external region. And what happens is, for example, here we have the results for M105, and this dot over here, which is more orangey, is the inner region, and the one that's redder is the outer region. And we can see that this distinction between the regions seems to also follow this trend. The thing is that to do that, you have to look at the inner regions of galaxies, which is always a problem. Like we saw before, it's just always going to be a problem because in the inner regions of galaxies, the surface brightness of the galaxy is just very, very bright, and even planetary nativity are quite hard to detect. That's why what we are doing is we are using a modified version of a method that was developed by Roth and collaborators last year, which rather than using the classical methods that we saw before, uses IFU, in particular us and them, we're both using Muse data. And the idea is that since Muse data, well, Muse gives us data cubes, and because we have a data cube, we can build whatever filter we want to build. We can just choose a wavelength range, we can choose a filter transmission function and build our own filter and get an image from that filter. So the idea behind this method is we can build filters as narrow as the spectral resolution allows us, which is very narrow. And if we look at images that are built from these types of filters so narrow, the signal to noise is much larger than if we just look at the O3 filter. So the idea is that we take what would have been the O3 filter and we split it into what we call slices, which are as tiny as the spectral resolution of Muse allows, which is 1.25 angstroms, which is super narrow. And we try to detect emission line objects in all of these slices. So we get something like what we see here, where we're just going through all of the slices that make up the O3 filter, and we are detecting stuff in all of them. We ask for objects to show up in at least 3 consecutive slices for them to be considered positive detections, because the emission line that we're looking for is going to take up at least 3 of these slices. So from that, we can get a sample like this one, and we can find objects that are very close to the center of the galaxy, were basically impossible to see before. Just as we are doing this on a pretty large sample of galaxies, we have about 15. I'm only going to show you the results for one, just to show you what the idea behind it is. This is a large-scale project that I am also slowly working on. But the pilot galaxy that we chose was in GC 1387, Fornax galaxy, because there is a very nice catalog built by Yellow Carburetors from 2018, which is over there, and we can see that they detect a lot of planetary nebulae, and they can go to very far in the extent halo, but in the central region, they find nothing. So if we zoom in that region and we plot our detections on top, we can see that we do in fact find a relevant number of planetary nebulae in that region. We can get their kinematics and look into that in the context of the larger kinematics. But with the main things that we...
Sorry, can we go back there?
Yes.
What is that central blob that you have on the right? That's not planetary.
No, it's just the kinematics of the stellar populations. Yeah, it's
you have, is it the same instrument that gives you the kinematics of the planetary nebula and the stars?
This one, yes, it's all Muse data.
It's all Muse data.
Yeah. So the two things that we are going to look at once we reduce our huge sample of galaxies are the luminosity functions. Our idea is not to get the distances, because we're only looking at a couple of planetary nebulae, but there seems to be a difference in the slope of the luminosity function when you look at inner region planetary nebulae and outer region one. So far, we just got the luminosity function for one galaxy, and all we can say is that the distance matches the one we find in the literature. So I haven't done anything horribly wrong yet. This has two slopes because it's completeness corrected, red one, and not completeness corrected, the gray one. But so far, we just have this slope, and we don't have the luminosity function for the outer region catalog, but we are working on that so we can actually compare it. And then, as I mentioned, we can get the surface brightness profile like we see over there in the black line, and we can see the planetary, maybe the number density, which are the blue crosses. We can calculate the offset between them, and that gives us this value of alpha that we're looking for. In this case, we find the value of alpha. That if we plot that one on this plot that I showed like 2 minutes ago, we can see that it does seem to follow the trend, and it does seem to be pretty close to the value of alpha for the inner region of M105, which is not something that we necessarily expect, but it's not very shocking. It should, if we can find all of the other 10 values for this, ideally we can see how the trend behaves overall. So just so we can move on to the pizza, the main ideas of this is that these tracers are very cool, and I really like them. Early type galaxies have a very large variety of formation histories across all environments, and it does help to look at their global cluster systems. And also that the relations between planetary nebulae and stellar populations have been widely used, but we still don't really know a lot about them in the theoretical sense. So it is vital to keep working on getting as many planetary nebulae as we can. Later on, some of the ideas that I'll be working on, hopefully during this next 3 years, we have some projects to look at late-type galaxies, because this has all been very fun. But late-type galaxies also have global clusters and planetary nebulae. They are significantly harder to find because there's a lot going on in late-type galaxies. There's a lot of emission, but we are developing some projects to try to detect those. And we have a bunch of spectroscopic data for all the global cluster systems that I mentioned before. So hopefully looking into that will give us some further conclusions. So that is all. That's where I am. If you want to talk to me, I am mostly always there.
A couple of questions. I don't see the Zoom window, so if you're on Zoom, just shout out your question.
Oh, I had a question.
Go ahead, James.
Just about the spatial distributions. Maybe I missed this. Were those red or blue or everything? Because I thought the red and blue ones are different, right?
Spatial distributions for
Of globular clusters.
oh,
Back sort of in the previous section. Sorry, forward to the those, well, the slide one back from that, the profiles you were showing, are those is that red or blue or everything? And would
no, they're just everything. I don't know why they chose choosing a red line for a globular cluster plot is not maybe the brightest idea now that I think about it. But no, it's just all of the clusters.
Okay, and but then aren't the red and blue distributions different on average, I thought?
Yes, but globular cluster systems as a whole, scaling relations are usually built considering the entire globular cluster system. Yeah, you can also look at them separately, but just the idea is that if you look at the whole system, you can get the whole size of the system. And what we're looking at the most is just the extension of the system.
Right. I guess I just wondered, when you're doing things like core radii, that it might be interesting to split them apart and see, is there any different systematic trend between the red and the blue?
Yeah, no, yeah, that's a spoiler on our upcoming work.
Okay.
Of course, it's there's things to see because red globular clusters are much more concentrated. There should be some differences there, but it is also hard to get good enough radial distributions for. As soon as you split the population in two, you have smaller numbers and your statistics are kind of worse. So that's taking a lot of more detailed work.
Okay.
Thanks very much. That's really interesting, but not my area at all. Are there many of any galaxies that have got large amounts of globular clusters and planetary nebulae in them that have been studied? And do those two trace the same things, or are they distributed differently? Galaxies?
Well, yes. To the first part, there's a few interesting works that look at both clusters and the planetary nebulae. Like just from the basis of what each of those objects are, they don't trace the same types of population because globular clusters are very old objects and they are stellar systems, and planetary nebulae are low mass stars, so they tend to trace maybe slightly younger populations. Usually, from what I'm very new to planetary nebulae, but from what I see, I think that they are maybe more tightly correlated to these types of properties of the stellar population that is right around them. With globular clusters, usually they formed 13 billion years ago, and then that's it, and they haven't changed, their metallicity too much. So you can find different information. Ideally, especially with the MUSE data, it would be nice to see if we can find where we find planetary nebulae, see if we can find globular clusters, but that's a whole different problem because you are in the very central region. It's just much more central than this. So if you find clusters there, they might just be nuclear star clusters, which are just a different beast that I'd like to get into, but not for now.
Great. I can smell the pizza's cooling, so I'm going to suggest that we can ask more questions over pizza. And thanks again very much. Great.